Hello, and welcome to AMAT362 at UAlbany, Probability for Statistics. This is Lecture 5. In the past few lectures, we've covered some of the basics of combinatorics, namely, how do you count the number of permutations of a word where they're repeating letters? We're going to use this to shed some light into our first lecture on conditional probability, which is again going to be one of the backbones of this course. So let's get to it. We're going to be talking about conditional probability. All right, this in some ways is just probability again, but we've incorporated some information. However, how information is communicated is a really subtle thing that takes a little bit of time to get used to. So let's start with our favorite sort of experiment. Imagine I have my urn, which we think of as sort of an opaque vase that has balls inside of it of different types or have different attributes. In this case, let's imagine I've got a bunch of red balls and white balls. So here I've got a total of 10 balls, 5, 6, 7, 8, 9, 10. And some of them are red and some of them are white. Let's say there are 4 red balls and 3 white. So, and 6 white. So we have 4 red, 6 white. In an urn. All right, what's our experiment? We're gonna imagine that we start drawing balls out one at a time. So here's our experiment. Draw balls out one at a time. Now, associated to this experiment, we have lots of possible outcomes, but let's identify some events of interest. Remember, an event is a collection of possible outcomes that make sense. And in the case of discrete probability, any possible combination of outcomes defines an event. So here are going to be 2 events of interest. Let's let E1 be the event where the first ball is red. And let's imagine that E2 is the event, E5 is the event that the 5th ball is red. So let's compute the probabilities of each of these events. So let's first compute what is the probability of event 1. Well, this has a really intuitive answer, right? I've got 10 balls, 6 of them are white, 4 of them are red. So I reach in, what's the chance of getting a red ball? Obviously it's 4 out of 10. Corresponding to the number of red balls divided by the total number of balls in my urn. How do we compute the probability of event 5? Because somehow we need to take into account all the possible things that could have happened ahead of time. So the question is, so we do first question, what's the probability of E1? We now have a second question, which is what's the probability of E5? So again, what is the sample space here? So the question is, what is omega? Well, one way of thinking of omega is it's going to be the total space of possible outcomes associated to our experiment, which in this case is I'm drawing balls out one at a time without replacement. I should make that clear. So without replacement. All right. So one way of thinking of omega is it's the space of all possible sequences. So let me think of this as all permutations of RR, R, W, 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 W. RAR. Actually, it's red, 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 white, 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 white. Corresponding to this would be the one particular outcome where I draw all 4 red balls in a row and then all 6 white balls in a row. Now, what's the size of omega? So meaning, again, we could have a world in which we draw a white ball, then a red ball, then another white ball, then another red ball, then another 2 red, and then whites. So by considering all possible permutations of this, we get to model our sample space here, which is the space of all possible outcomes. In this case, we know that the size of omega is equal to 10 factorial divided by the number of reds factorial, which is 4 factorial, and the number of whites, which is 6 factorial, which is equivalently 10 choose 4. Or by our principle of duality, it's 10 choose 6. Either way, this is a pretty large number. So how could we use this framework to compute the probability of E5? Meaning I have a 5th ball in a red ball in my 5th position. So here's a way of modeling that. So E5 is going to consist of the subset of all permutations where there's a red ball in my 5th position. So these are going to be permutations of this right here, where there's a red in the 5th position. How do we compute that? Well, all we're doing is, again, we've got 1, 2, 3, 4, red in my 5th position, that's 5, 6, 7, 8, 9, 10. So we have another ordered sequence of possible draws, which corresponds to, all right, well, I've got now 9 remaining balls. So here these X's correspond to the 9 remaining balls. With, well, we've used one of the reds. So now there's 3 reds and 6 whites. Sorry, 6 white balls. So what's the number of permutations of what's left after I've fixed red to happen in my 5th position? Let's go over here to just do it real quick. So number of perms of 6 whites and 3 reds is equal to 9 factorial over 6 factorial, 3 factorial. So what is this? This is the number of ways in which our event E5 can occur. And the probability is going to be the ratio of these 2 numbers. So probability of E5 is going to be the size of E5 divided by the size of omega, which corresponds to 9 factorial over 6 factorial, 3 factorial, 10 factorial over 6 factorial, 4 factorial. Well, it looks like a lot of cancellations could be made here. Again, let's just go ahead and simplify this fraction, which you all should remember corresponds to flipping this upside down and putting it next to this over here. So how does that work? 6 factorial times 4 factorial over 10 factorial. And again, I can just think of this as multiplying by 1, knowing that this is all going to cancel. And now we've got a lot of cancellations that can be made here. All right, what do we got left? Wow, okay. Well, notice if I cancel 9 factorial into 10 factorial, that's going to leave 10 left. And similarly, 3 factorial into 4 factorial is going to leave 4 left. So this ends up equaling 4/10, which is exactly the same probability as event 1. Probability of getting a red ball on the first try is equal to the probability of getting a 5th ball or a red ball on the 5th try. So probability of first ball red equals probability of 5th ball red. Does that answer surprise you? So let's think about a related question. Imagine I have a deck of cards. What's the probability that the top card is the ace of spades? Well, there's only one card that is the ace of spades, and I've got 52 possibilities for that card, so it's 1 out of 52. What's the probability that the last card in the deck is the ace of spades? Assuming we don't know anything else about what's the first card or anything else between. Well, let's think about it. I just ask you, what's the probability that the last card in a shuffled deck of cards is the ace of spades? It would also be 1 out of 52. So this tells you that as long as you don't have any information about what has happened before, actually the probability here doesn't change. But somehow intuitively, we think that because more stuff has happened, the probability needs to change. But if we don't know what happened, then we're just gonna forget about it. All right, so important lesson here. I'm gonna go ahead and put this in blue. So here's the upshot. So as long as we don't know any information, the probability of the first event doesn't, in this case, affect the probability of the 5th event. So let me just say this slightly differently. Unless you know what happened before, can't include it in computing probability now. And again, this is a weird answer. I want everyone to sort of take a moment to just sit and reflect on this answer right here. This is asking, what's the probability that the 5th ball drawn out of an urn where there are 10 balls, and there are 4 reds and 6 whites? What's the probability that the 5th ball drawn is a red ball? In many ways, this number here does not make any sense, because by the time you go to draw that 5th ball, there should only be, say, 6 balls remaining. Let's see if I did that calculation correctly. Yeah, so here I am. I've already taken away 4 balls. I'm about to take my 5th ball. That means there are, 6 remaining. But in what percent of those balls is the red one? Well, we don't know, because we don't know what's happened back here. So this was the calculation I did with all the permutations sort of the long way. And if you start to develop an intuition for probability, you'll have a better sense of like, well, I could just disregard that and just know that, when I reach in and I don't have any information, I know that 40% of the balls are red. So then that's my chance, my probability. We're going to start to see now how probability of E1, where I draw a red ball, affects probability of E5. This is all expressed using the framework of conditional probability, which is the main subject of today's lecture. So here we are, conditional probability. Conditional probability. All right. So basically, this is the thing, this is the tool that allows us to update our calculation of odds to incorporate information. So let's go ahead and write this out. So here's our definition. If B is a subset of our sample space omega, we think of this as an event. So if B is an event, and let's assume that the probability of that event is greater than 0. In some sense, if we're going to take into account for something that's actually happened, we need to assume it has some chance of happening. Otherwise, we might get some silly answers. And you'll see why right now in the definition. Then the probability of A, an event, given the information B, that's how we need to read this right here. This is the probability of A given B. So it's the probability that A occurs given the added information that B occurs is defined to be equal to probability of A and B occurring divided by the probability of B. So this is a general definition, but let's go ahead and specialize to the setting we just used it in. So here's our special case, which corresponds to uniform probability when omega is finite. Here we think of probability of A given B as being the size of each of these events. So again, remembering that these vertical bars indicate the size notation. Let's do an example. Continue from above. Suppose we want to compute probability of the 5th ball being red, given the information that the first ball was red. I'm going to show you 2 ways of calculating this. But let's go ahead and just write out the definition again of conditional probability. It's probability of both of these events occurring divided by the probability of that given event occurring. So let's do this the long formal way. So here's the long formal way. The long way looks something like this. So imagine I, again, have my 10 possible draws, because this is all drawing without replacement. And let's fix the setting where I know that a red ball occurred in both the first and fifth position. And so here I've got different possibilities, but all I know is that of these remaining 8 balls, I've got 2 red and 6 white. So here and here combined together, I have 6 white and 2 red. So computing the probability of both E1 and E5 occurring, which is considering what's the space of possibilities where both the first and the fifth entry in this long word are all red. Well, it just accounts to computing the number of permutations of what's left. So said slightly differently, probability of E1 and E5, which is the same thing as the probability of E5 and E1, because set intersection is symmetric, is given by the number of permutations of 6 W's and 2 reds, which is 8 factorial over 6 factorial 2 factorial. It's also written as 8 choose 6 or 8 choose 2, whichever way you like. In this case, numbers are starting to get smaller, so we can say it's 8 times 7, which is 56, divided by 2. So what does that work out to be? Should be something like 28. Of course, yeah, 4 times 7 is 28. So that's the number of ways in which this can happen. Of course, I need to divide by again, my sample size omega. So let's divide by my 10, choose the 4 positions for the reds, which again is a fairly large number. Let's see if I can go ahead and do it on the fly here. So let's simplify. So probability of E1 and E5 is equal to, well, what do we already figure out here? We had 28 over, well, 28 over 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. All right, so let's keep working here. All right, I've got, well, let's cancel away the things that we can do. So 4 and 2 goes to 8, 3 goes into 9 3 times. And I think that is basically it for the denominator. So now I've got something like 28 being 4 times 7 over 10 times 3 times 7. Now this is going to look a little weird, of course, as I cancel this out, but I'm going to write it slightly differently. So 4/10 times 1/3. Another way of writing this is as 4/10 times 3/9. And if I'd simplified slightly differently, I would have gotten exactly this 3/9. Now this actually makes sense. Why does it make sense? Well, this is the probability that the first ball is red. And let's just imagine that I was just computing now the probability that, say, the second ball is red. This is the probability that the second, and I'll call it observed ball, because we didn't observe any of the balls between 1 and 4, or 2 and 4, I should say. Observed ball is red, given that one red has been removed. And that kind of gets at exactly the easy way of doing this. So the easy way says something like, all right, if I want to know the probability of E1 and E5, meaning first ball and the fifth ball red, I just take probability that the first observed ball is red, it's 4 out of 10, times probability that the second observed ball is red. Well, I got to remove one ball, red ball, and so that's 3 out of 9. Now, the fact that I was able to double check this intuition using the theory of sort of permutations of a word with repeated letters should hopefully give you some comfort that this is the correct answer. And again, even though this is sort of long and slow, in some ways you feel more certain that this method right here isn't going to lie to you, even though it's a little more complicated. But eventually you'll be able to just use your intuition and go straight for this, knowing that you can always back your reasoning up using the more extended computation. All right, so let's highlight, again, the final computation, which is, I want to know what's the probability that my fifth ball is red, given that my first ball was red. We already computed the top, probability of E1 and E5 occurring. Now we need to divide it by the probability of E1, which in this case ends up equaling, so again, we had 4/10 times 3/9 divided by probability of E1 occurring, which is 4/10. These cancel, and we get that the final answer is 3/9, which again makes perfect sense, right? I don't know what's happened before. So there's sort of 9 unknown balls. I've already taken one of the 10 out and I know it's red. So of the 9 unknown balls, I know that 3 of them are red. So the chance that I'm going to pick one out that's red is 3/9, or 1/3, or 33%. Repeating, 0.3, repeating. So again, hopefully this all actually kind of makes sense. Now let's give ourselves some rules, because we're going to want to be able to use these kind of techniques again and again. So I call this the multiplication rule. And it looks something like this. So we know that the probability of an event A, given that B occurs, is equal to the probability of A and B divided by the probability of B. But we can also reverse this by then saying that the probability of A and B occurring is the probability of A given B times the probability of B. Which really is the way we tend to think about how to compute this and probability. It's like, all right, well, I want to know a situation where both things occur. So one thing I could do is, well, let's assume that the second thing occurred, in this case, B, or drawing our first ball being red. And assuming that knowledge, let's now compute the probability that A occurs. And that's expressed using this conditional probability notation. And then by multiplying those answers together, what's the probability of A occurring given that B occurs times the probability that B occurs? That recovers for us the probability of A and B. All right, so let's consider a slightly fancier version of this rule. So there's also a iterated multiplication rule. Iterated meaning you're just now going to consider a whole string of events occurring. So let's suppose we've got a collection of events, A1, A2, all the way down to AN, where the probability of all these events occurring is non-zero. And one way to get at this probability is that the probability of A1 and all the way A2 and A3 all the way down to AN occurring is equal to the probability of A1 occurring times the probability of A2 occurring given that A1 occurred times the probability of A3 occurring, assuming that A1 and A2 occurred, all the way up through the probability of our nth event occurring, given that all the previous events occurred. So you can see this is sort of the stretched out version of this rule up here, but now where we can condition on multiple things occurring. This all might seem really scary, but we're going to actually simplify, get so used to it, you're going to even forget that it had a special name. So let's go ahead and do an application relevant to the example we've just been playing around with. So we've already computed what's the probability of our fifth ball being red, assuming that our first one was red. Maybe let's dial it back a little bit and just consider what happens as we draw one ball at a time. Suppose I want to know what's the probability that my first three balls are red. And now I'm going to do it really simply without any of this permutation nonsense. All right, let's get to it. So example. So it's the same urn that we have before with our 4 red and our 6 white. All right, 6 off white. That's our urn. Let's compute the probability of our first, second, and third balls being all red, drawing them out one at a time. So this is first, second, and third balls are red. Well, this is the same thing as the probability of the first ball being red times the probability of the second ball being red, assuming that the first ball was red, and then multiplying all that by probability that the third ball is red, given that the first two were red. Again, it's going to seem easy as pie. Probability that the first ball is red, it's obvious, it's 4 out of 10. Now what's the probability our second ball is red, assuming the first ball was red? There's no doubt, we've got 9 balls left. 6 of them are still white, only 3 of them are red. So that means we've got a 3 out of 9 chance that that second ball is red. What about the third ball? Well, we're assuming, what this means right here is we're assuming the first 2 balls are red. So we've only got 8 balls left. 6 of them are still white because we haven't picked any white balls yet. And then I've got 2 red left. So 2 out of 8 chance that that third ball is going to be red. And this exactly expresses the intuition that we've been using all along with, well, what's the probability of a 4 of a kind? What's the probability of, getting 3 kings in a row? We've been using this kind of concept or reasoning implicitly without using the name conditional probability. So this is easy. All right. So let's go ahead and take this up one more notch. Let's get something that's going to be a setup for problems that we're going to consider again and again and again. Slightly new setup here. So let's consider the setting where we've got not just 1 urn, but 2 urns. So we've got 2 urns. And for those of you who like history of math, these are sometimes called Polya urns, named after famous mathematician and physicist George Polya. Anyhow, let's go ahead and think of this as urn number 1, and this is urn number 2. And we've got, in addition to our original setup here, where we had 4 red balls and let's say 6 white, we've now got a slightly different urn where there's 7 white balls and 3 red. So the same number total of balls in each urn, 10 namely, but where the ratios are slightly different of number of reds versus number of whites. So here's the kind of question that we ask in this setup. And right now it feels contrived, but I'm going to show you in another lecture or two how this kind of shows up all over the place. So here's the question. And here's, first of all, the experiment. So the experiment. Because now we can't just say, let's reach into an urn and draw out balls without replacement. We've got 2 urns to pick from. So we need to incorporate that into our setup somehow. So here's our experiment. So I'm going to randomly, and of course that means uniformly at random, select urn 1 or 2. And then I'm going to pick out a ball. Then pick out a ball. Now, what's the probability of getting a red ball? So here's the question now. Well, obviously, anybody that you'd talk to would say, well, it depends which urn you picked. How do we incorporate that information into our computation? We have to use conditional probability to set this up. And let me show you a really useful tool for organizing this information. Kind of goes to sometimes called decision trees, but it's just a good way of branching or mapping out the whole forking paths of possibility. So first of all, here we are. We haven't done anything yet. One world, we're going to pick earn 1. So this is our earn 1 world. I'll call it U1. And in another world, we're going to pick earn 2. If we're assuming that we're picking these earns uniformly at random, so we flip a coin, heads for earn 1, tails for earn 2, the probability of each of these paths is a half. And just to give this a name, we'll call this as the probability of U1 equals a half, and the probability of earn 2 is a half. And so now, conditioned on this information, we can then sketch out our possibilities. So here I've now got, again, 2 possibilities when I draw and pick one ball out. One world I get a red ball, and in another world I get a white ball. So here we have red, red, and then here we have white, white. Now, what's the probability of going down each of these paths conditioned on the information that we chose earn 1? Well, in this case, we can say, the way we write it is that the probability of a red ball given earn 1 is equal to 4 out of 10. Because there were 10 balls in earn 1, 4 of them were red. And over here, the probability of a white ball given that we picked from earn 1 is going to be the complement, 6 out of 10. Similarly, over here, we get the probability of a red ball, assuming we picked from earn 2, slightly lower because there are only 3 red balls. And then over here, we've got the probability of white ball, assuming we picked from earn 2, to be the complement, which is 7 out of 10. So we now can compute what's the probability of picking out a red ball. Well, we need to figure out there were 2 different chains of ways of this happening. And the way we can express that information is like this. So now we want to say that the probability of a red ball is going to be equal to the sum of 2 probabilities, one where we picked from a red ball that came from earn 1. So let's say it's red and earn 1, plus the probability of red and earn, and earn 2. But to compute these probabilities, we need to use the multiplication rule, where we took together, well, first I need to figure out what's the probability I went down this path, and then the probability down this path. So that's going to be 1/2 times 4/10. It gives me a 20% chance of walking down that path, because 4 divided by 2 is 2, so I get 2 out of 10. Similarly over here, we then get a 3 out of 20 chance, which is still a little bit smaller than that in this case it would have been 4 out of 20 chance. But again, we could have gone down either path. All we're interested in is what are the number of ways in which we arrive at these 2 red balls. And by summing these 2 paths together, we get our total probability. So writing it out, the probability of red given we picked from earn 1 times the probability of earn 1, plus the probability of red given that we picked from earn 2 times the probability of earn 2, which, as I just indicated, is 4/10 times 1/2 plus 3/10 times 1/2. And so adding these up together, we end up getting 7 out of 20. Which in this case actually makes perfect sense. Imagine I had poured all my balls together into one big urn. There'd be a total of 20 red, or 20 balls, 7 of which were red. Now, that's a common mistake that we'll focus on again in later lectures and exercises, because I could have changed the number of balls in one of my urns, and this method would still work, but that more intuitive method, that would have led you astray. You would have gotten the wrong answer. But let me go ahead and sum this all up with one really important principle. I'm going to call this the law of total probability. This is the law of total probability. And it's so important, I'm going to give it its whole scroll of possibilities. You see the little paper curling up here. All right. So the law of probability says this. If B1 through Bn partitions my space of possibilities, omega. So the picture you want to have is something like this. B4, B5, B6, B7, B8, B9, so on and so forth. And I know that the probability of each of these events is non-zero. Then we can compute the probability of any event A as follows. Probability of A is going to be equal to the sum from I equals 1 to n of the probability of A and BI occurring. Now we can combine this with the definition of conditional probability to get the following, which is that the probability of A is equal to the sum of a bunch of conditional probabilities. This is the probability where A occurs given that BI occurs, of course, times the probability that BI occurs. And so here we imagine that we've got some event A, which overlaps all these possibilities. But in order to compute the probability of this event, and again, you should think of probability here as area or size, it makes perfect sense that you could just sum up the little intersections of each of these pieces, and then you would get the probability of that event occurring. All right, so that's it for today. I look forward to seeing you all in lecture.